Welcome back to our course on fluorescence spectroscopy. Uh, this is going to be the second lecture on fluorescence polarization immunoassays. We're going to cover a number of diverse topics today, but they sort of relate, of course, they relate to what we did in the part 10A. In part 10A, we finished up with showing how complex a fluorescence polarization immunoassay can be to prepare because of the number of chemical components that need to be made. And we're going to continue with that today and also going to explain why these complex assays are used, which is not always obvious. So why talk about the FPIs now? Well, we just finished lectures on 9 on polarization and anisotropy. These measurements use another class of instruments, the microplate readers. You may or may not be familiar with them. Recently, new opportunities have appeared in FPIs, and it's just an enormous business. Boy, I wish I would have gotten into these FPIs earlier when I first saw them published, but of course, I always missed good ideas. So, FPIs are performed for almost any type of biomolecule. If you're going around the list here, you have nuclear receptors, kinases, enzymes, ion channels, blah, 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 secreted proteins, and then they break them down. So it's such a powerful and generically useful method that FPI has been made for almost everything. The dominant use of the competitive fluorescence polarization immunoassays has been drug discovery. And the problem with drug discovery is, let's say you're looking for a new drug that's going to help your heart or something like that. We'll see an example of that later. And you have to screen thousands of compounds because the drugs that you're going to be looking at are probably about 500 Daltons. There's at least 10 to the 22nd possible molecules of 10 to the 20 Daltons. You could never get them all, and you could never test them all. So this has resulted in a whole industry, which is called high-throughput screening, where many of these materials are put on microtiter plates, and many are tested at the same time. And from this, they break it down to a small number of compounds that are worthy of further investigation. This requires, first of all, you have to synthesize these many analogs that you want to test. You can't just go buy them from Sigma or Aldrich. So you have to test thousands of molecules. I can't find a complete list of the unique number of FPIs there are, but there's at least 1,000 that are approved for use. And the cost to go through all of this stuff to bring a small molecule drug to market is anywhere from $1.3 to $1.8 billion. No matter how you adjust it for inflation, that's still a lot of money. Even more interesting is the amount of money that is spent on fluorescence polarization immunoassays. I can't swear by this 100%, but from what I can tell, the cost of development and the cost estimates for doing the assays were listed separately. So the cost per test in the USA are 20 to 50 bucks. Worldwide, they're not very different. The number of FPI tests that are performed per day are in the tens of thousands, or worldwide in the hundreds of thousands. So the annual expenditure on the testing itself, even after the FPIs have been developed, is anywhere from $500 million up to $4 billion, depending on whose estimate you take. So it's a really big industry, and it doesn't seem like a very difficult technology, but it can be difficult to implement. This is something that has always amazed me. All of the FPIs are performed using short lifetime fluorophores, 1 to 5 nanoseconds. You go around here, you see Badipis, Alexas, Texas Red, cyanins, blah, blah, blah. These are all the traditional probes that have been used for FPIs. And you would think with spending that many billions of dollars a year, that the companies would spend some money on the probe chemistry, which they don't seem to do. We'll see in the next lecture on FPIs that there are reasons to have longer lifetime fluorophores, but I guess it's just tradition. These are the ones they use, even though at the same wavelengths you can wind up with perhaps more favorable probes for FPIs. Many of the microtiter plates that are used are designed for FPIs. Trying to stifle a sneeze here. The microcanal plates can have anywhere from 384 to 1536 samples. Maybe I reversed a number there. But anyway, so you can do a large number of tests at one time. And these are the experiments that are called high throughput screening. These microtiter plate instruments are extremely versatile, and it's almost shocking, coming from when I started with fluorescence spectroscopy, and it was so difficult to measure one wavelength at one emission intensity at one excitation wavelength and get the same answer the next day. But these machines have advanced tremendously, and not only do they do FPIs, but they can do absorption measurements if it's an absorption assay. They can measure fluorescence from the top or the bottom. They can measure energy transfer as well as polarization and anisotropy, luminescence assays, and others. But there's one special thing about these instruments that I wanted to bring your attention to, because all of the fluorescence polarization measurements we spoke about used L optics. That is, the excitation was along one axis and the observation was on an opposite axis that was perpendicular to that. And that's going to be so how do you get a G factor? We knew, well, let's see, the instruments are complicated. As I discussed in the second lecture, I think it was on instrumentation, every optical surface is going to polarize the light to a different amount. So it's going to be very hard to know what the light polarization is going through this complex set of mirrors in these instruments. So the question for me was, how the heck do you determine the G factor in these instruments? So I went back to basics and I looked at how we did it in the L optics. We excited the sample with vertically polarized illumination, got this figure 8 excited state distribution. So that had some particular intensity in the parallel and perpendicular channels. And then we rotated the excitation beam horizontal, and we knew theoretically that gave us the same amount of light, both parallel and perpendicular, because it's an on-axis measurement. And when we measured those two intensities, we could get the G factor and proceed with calculating the corrected anisotropy or polarization. How do you do that with straight-through optics? Actually, it turns out it's not too hard, but let's look at the straight-through optics first. We have a fluorescence microscope we have some light coming in. It's going through a dichroic filter, and some of the green light is getting reflected down here, and then it's fluorescent, and it goes through the filter. The filter is chosen to reflect one wavelength, let the other one pass, and it has some polarization up through here. Something that's very critical here is the emission filter, because you have a lot more stray light to deal with when you're in this straight line optics than we did in the L optics. The incident light, here we really had an unknown polarization. We didn't know what it was. So the very clever trick was to take a sample with a very low or zero anisotropy. And that's not hard to get. If you put rhodamine or fluorescein and just put in ethanol, the fluorescein is essentially close to zero, or darn close to zero. So the way you determine a G factor in a microscope, even a confocal microscope, is to put in a sample with low anisotropy and then measure the intensities at your two detectors, which are through polarizers oriented at different places, different orientations, and that will tell you what your G factor is for the measurements. So we spoke about using the competitive immunoassays in drug discovery. In more recent years, there's been a very different use of immunoassays, which they're non-competitive or direct immunoassays. You might remember in the first lecture of this series, I said how these names overlap, and we can't always just call them by one thing. Sometimes they're simpler. This is the beauty of it. They're simpler assays, can be done in a microtiter reader, but they could be dedicated portable devices, even cell phones. We don't need to label the antigen that you're looking for. You might remember in the competitive FPI, we always had to make a labeled drug. I always think a direct assay is more reliable than a competitive assay, and as we'll see in a few moments, these non-competitive immunoassays can be used in whole blood or serum. They're also homogeneous assays. So, the stuff is in suspension. So then we come to the question. In fact, I just thought of this as I was preparing this lecture. And I asked myself the question, if the non-competitive FPIs are seem to be so much easier up front, why are the competitive assays used so much in drug discovery? And I guess you'll catch the typo there. It should be drug. And the reason is, at least this has to be the reason, a change in polarization will always change with molecular weight. That's just the way it is. It might change a little bit, it might change a lot, but if something happens in the sample, it changes the molecular weight, and that somehow involves the labeled molecule. You can be sure you're going to get a change in the molecular weight. You can't guarantee this with something like FRET, because with FRET, first of all, you need two labels, and secondly, they could be close together between the complex or far apart in the complex. So a FRET assay is not guaranteed, but a change in polarization will always occur, and the polarization assays being ratiometric measurements can be quite accurate. Some of the ones I'll show you seem to have very low changes in polarization, but I'm sure that will be improved in the future. So what do we mean by a direct non-competitive immunoassay? We have one here. It's directed against HIV antibodies in human serum. If you get HIV yourself, your body will make antibodies, and many of the antibodies that it makes are against the spike protein on the COVID virus. Now, here are the results of the assays, negative and positive. They're not wonderful. You would hope for more discrimination than that, but they can distinguish positive from negative. The results of such an assay can be attained in a very short period of time, and the antibody, let's see, the human serum is mixed with the labeled antibody against the receptor binding protein, and that slows down the rotation of the labeled, so what's the domain called? We'll see it on the next slide. Receptor domain. This figure I found extremely confused. I looked at it many times and I decided to remake it for easier understanding. So here's how that assay is actually performed. An individual becomes sick because of COVID virus, and spike proteins are released into the blood. So there's the antigen you're going to be looking for. Might not be a lot. I guess these are hard to look for, but what are easier to look for is that what the patients themselves do. The patients are going to be making antibodies to the spike protein. So having antibodies to the spike protein means that you have been infected with COVID. So what can we do with this? I think it's called the receptor binding domain. It's only a small part of this protein here. We use that as our tracer molecule for this assay, and label it with anything. It's some red dye here. And then we take a sample from the patient. You mix a sample from the patient with this labeled material. Before there's any antibody there, it's rotating quickly. So it has a lower anisotropy. But if the patient has an antibody to the receptor domain, it's going to be a much slower rotation when it forms this complex, and that's the origin of that higher anisotropy we saw in the previous slide. So I thought I'd save you the trouble of trying to look through that previous slide like I did for hours before I just decided to redo it. Now, one of the problems with these direct immunoassays is that you may not get a large enough change in polarization when the antibody binds to whatever the antigen is. So the answer to that is to make the tracer molecule smaller. So when you get an antibody molecule complete, it's something like this, 150 kilodaltons, and it's very easily broken up into smaller fragments. And these FAB fragments, as they're called, actually an FAB fragment would be a combination of these two. The FAB fragments have all the same specificity that you had in the original protein. So now you have something that's, 6-7-fold smaller than the original IgG, which can serve as your tracer protein. Once again, the value of basic science. Way back in 1949, Rodney Porter figured something like this out. He did, and why would you do this? He did a enzymatic digestion of the IgG antibodies, and he noticed that he had an active component that was a much smaller size, and it still had the same antibody activity. So this resulted in Rodney Porter getting a Nobel Prize. I don't know which year that was. By the time when I got to Oxford in 1972, trying to do NMR, which proved out to be not the best choice for me. I can't give you details, but I was really proud of this because I got insulted by Rodney Porter, the future Nobel Prize winner for the digested fragments of IgG. I don't know why it made me proud, but we met later. We had a long, friendly discussion about the human complement system. It was just a simple misunderstanding, but when you get chewed out by a Nobel Prize winner, you remember it. So that's why I mentioned it here. So let's look at some non-competitive immunoassays. Here's ones for an influenza virus. And this is why they're convenient. The target antigen does not need to be labeled. You take your sample, you have a great big viral protein, and in this case, the authors used an FAB unit because it's smaller and will rotate faster. If you have no virus in the sample, you're just going to have this quickly rotating FAB unit, and the polarization is going to be low. If you do have virus in the sample, some of these FAB units are going to bind to the virus, and it's going to slow down the rotation, and the anisotropy is going to go up. Actually, this was a pretty pathogenic virus. This could be a very quick assay with modern optics and technology. But once again, I would hope that when it's further developed, they would get larger changes in polarization. This is a neat one. Test for C-reactive proteins are very frequent in emergency rooms because someone walks into an ER, the usual complaint is chest pain, and the cardiac markers are one of the things that are predictive for a heart attack if you have elevated CRP. But there's another thing, sepsis, pneumonia, a whole variety of things can result in elevation of the C-reactive protein, and many of them are dangerous. In a routine analysis, someone in a hospital bed, you might send it to a central lab, and it might take a few hours to get an answer back. But in a point of care testing, you need results in 3 to 15 minutes. If you want to know if the person has an angina, if they need to use an anticoagulant, or if they have an infection, because infections can easily be fatal. So we needed a rapid point of care testing for the C-reactive protein. Here are the results, not for the rapid testing, but for what the molecules are. FAB is the label. I don't have a label here, I'm sorry, because we don't have a fluorescent label, about 60 kilodaltons. The C-reactive proteins are surprisingly large, on the order of 115 kilodaltons. They're pentameric proteins. And if this labeled FAB unit binds to here, you know you're going to get an increase in anisotropy. And this is what I said, these anisotropy assays are popular because you know they're always going to give you an anisotropy. So here are the delta P values for this assay done with FAB and with IgG. And as you can see, the delta P that's done with the smaller FAB unit is several times larger than you get from the full IgG protein. If you look at this closely, I don't think these should have been the same at 0 CRP, but I think the data were normalized at this point, and so you can show them the same scale. So the FAB units give you a larger delta P for this assay for C-reactive proteins. And a point-of-care device has already been published for rapid CRPs. Right now, I think, compared to what's going to happen in the future, it's maybe a little bit complex, but it reacts very well to CRP with a rapid reaction time. And if the sample is injected, there's an enzymatic reaction that goes on in with the sample. It changes a non-fluorescent molecule to a fluorescent molecule, and there's many light sources you can use. You can use a laser light source, or you can use a flat light source by cutting a little 1-inch square out of your TV screen. That would work just as well. So I think we'll see many more point-of-care assays of this type. Well, that's it for 10B. I'm going to do a 10C. It seemed that probably the shorter lectures were going to be more useful to you all, so I tried to break them up. And in a little while, we'll be putting together 10C, which has some extremely interesting developments in immunochemistry.